that, or why we use Morse potentials.
Good personally.
Okay. So in that case, I'll just move on, and we can go straight into to a different Excel document. Aren't you lucky? So here I've just collated the parameters from the previous slide. These are from your table of parameters, but they are actually just universal physical constants. You can just use those. And then these are the values of d0 prime and de prime that I just found in my previous spreadsheet. Next step is to convert those to kilojoules per mole. Can someone just talk me through how you're supposed to do that? There's a big hint across the top here.
Yeah, you convert to hertz to joules, kilojoules per mole. So to convert to hertz, you times by the speed of light.
Yeah, but you've got to be careful about your speed of light. Why?
It needs to be in meters per second.
Well, you either need to convert your wavelength into meters per second or your speed of light into centimeters per second.
Oh, yeah, sorry.
So you, to cancel the per centimeter with the centimeter and leave you just with the per second, you need to have 3 times 10 to the 10 here for your speed of light in centimeters per second, and that will give you a frequency that is correct. And then to convert that to joules, you've got per second times Planck's constant, leaves you at joules. And then finally, to convert to kilojoules per mole, you times by Avogadro's constant and divide by 1,000. And that gives you something around 50. So racing forwards, this is where everyone starts to get a bit unstuck, is calculating E star. And the reason that people tend to struggle here, I think, is because the hint is, to a certain extent, not accurate. So the hint gives you one way to do this, but it turns out that that's the hard way, and there's a much easier way of doing it. So if we look at the diagram I've put up on the right here, we're trying to calculate E star, which is the energy difference between the ground's electronic ground vibrational state and a fully dissociated iodine molecule in the excited state. But to do this, we can use parameters that we've been given. So if you look in your table of parameters, you've been given EI star, and you've been given DE double prime, and you're also given omega E double prime, from which you can calculate D naught double prime. So E star is, well, let's write it out in full. E star is going to be DE double prime minus omega E double prime divided by 2, which is a 0-point energy. So that gives us D naught double prime effectively. Plus E I star, so the energy of exciting one iodine atom. So I plugged that all into Excel, but obviously you can do that by hand. So to get E star, I've got D naught star here. I've already calculated the 0-point energy. That's just omega E double prime divided by 2. And that gives you D naught prime and then E star, and then convert those into kilojoules per mole. You get 240 and 150-ish. So that was a sort of race through, but would anyone like me to go back through it?
No, but can you give me 2 sets? Just copy that up.
Yeah, of course.
Cheers. Wait, so D double prime's given to you, and so is the WE double prime.
Yep, so you get DE double prime and omega E double prime and
Oh, okay.
I star.
x.
What do you mean? Well, your value should be inside the error of theirs. But you don't have to do this because I don't think this is a report one, is it? So if you were doing, yeah. So you're told that you've got an error between 2 and 4%, and we'll talk in a second about how you should be dealing with that. But in terms of your values, you don't need to put errors on them. Calculating errors and propagating errors through this experiment gets quite involved because of all the different mathematical operations that you put your measurement through, not least of which is least squares regression. I mean, you got an R-squared value of something around 0.9. I think you got a slightly better one because you deleted some data points. That means you've basically got a 10% error on the line. It turns out it's slightly less than that. I don't really know how anyone arrived at the 2 to 4% interval, but we'll just talk about it in a second. Okay, so the last part of the pre-lab work is to calculate nu naught naught, and you should be able to do that fairly swiftly because you can see that nu naught naught here. Let me get this. Nu naught naught is E star minus D naught prime. And you don't need to do any unit conversions on that, so that's 1600 waveforms. Okay, so we're pretty much bang on time-wise. I'm just going to go through a couple of the points. I think someone asked at the start about eliminating data points, or is that a different group? Great. So in terms of eliminating data points, that is a hangover from when this experiment was done in person. So instead of having that nice colorful spectrum that Frank showed you in the video, not if you saw the video, you can see like a dark outline against a rainbow spectrum. That's a digital spectrometer. And in the past, we were using analog spectrometers, which didn't require power source at all. They're actually quite an elegant experiment where you shine the light through a prism and it scatters, and you change where you're looking at in the scattered light by rotating the prism and calculate the wavelength that way. That obviously leads to a lot of outliers because you get quite a lot of noise in an analog spectrum. And that's where that part of the experiment comes from. So you can obviously eliminate data points to make your line of best bit bigger, and you're told to do so. However, if you're removing data points, you need a reason. Your reason should be better than I expected a straight line, so I removed all the points that didn't fit the straight line, even though that's what obviously you were told to do. That's not a great scientific method to just eliminate the data points you don't like. That hasn't been standard practice for about 150 years. So we need to think about, because I noticed you did eliminate some data points, what they might be coming from. Does anyone have any ideas? Yeah, so there's noise, but that doesn't necessarily affect your measurement because you're taking a peak. So the experiment video, you get a big lump, and superimposed on that big electronic transition, you get little peaks corresponding to the vibrational transitions. Yeah, so the peaks will overlap slightly, but also if you get low signal to noise on one of these peaks, you might accidentally miss it out. How would that affect your data? So just using this this missed out peak here I've done in blue, you should get 2 delta E values like this, but you actually only record 1. How big is that going to be relative to these ones? Yeah, it's going to be effectively twice what you want. And then the other thing is you'll be numbering wrong. So if you do 23, 24, this one should be 25, but you would actually be labeling this one as 25. So that's one source of error, is missing out peaks because of noise. But there's another source of error. And here we draw yet another Morse potential. Ground state in red. Excited state in blue. So most of your transitions, I'm going to do this in green. Most of your transitions will come from nu double prime is 0. So if you're at 0 Kelvin, this is the only vibrational state that would have any population at all. And you would get transitions that were like this, directly from the ground vibrational state to the excited electronic state. But because you are not at 0 Kelvin, you also have thermal population of the first excited vibrational state, the second and the third, and so on and so on. So you're also going to get transitions to the same point, which have less energy. So what you're going to get is a spectrum where you've got these green peaks coming through more intense, and then distorting those, you're going to have less intense pink peaks with lower intensity and an energy shift of whatever this is, something similar to omega E double prime. And that's going to distort the data. So incidentally, these pink peaks we call hot bands because they derive from thermal population of low-lying excited vibrational states. So that's 2 potential causes of outliers, and they're the 2 that I consider to be the biggest causes of error for this experiment. Is there any more questions about outliers and errors? So resolution is more about precision and accuracy. So accuracy is closeness to the true value, and precision is where you really get your significant figures. That is going to be a problem, but I think it's more like those wavelengths were recorded to 6 decimal places. So they're quite precise. Whether they are accurate is the question. As in, are they where they should be? Okay. So just before we move on to the post-lab work, let's just think about errors. So you got values for d0 prime. It's basically the same as de prime, approximately 50 kilojoules per mole. And you're told you have approximately a 4% error. So question 1, what's 4% of 100? What's 4% of 50? So you basically have your d0 prime and de prime values. It's something about 50, basically plus minus 2. How many significant figures should you be reporting that to? Yeah, 2 or 3, right? So if you go back to my example, I had, say, 54.137625 kilojoules per mole. Why is it bad for me to report my my data to 6 decimal places? So this implies I've done a much better experiment than I've done. It implies that I know the answer to a much higher number of significant figures than I actually do, when in fact the answer could be anywhere between 52 and 56. So really we should be reporting either 54 dead on or 54.1. And it's important to do that, especially for your table of parameters. Let's have a look for you guys. Yeah, so for this experiment, if you report to 2 significant figures, most of your values will be pretty much the same. So I'd recommend using 2 or 3, 3 if you want to be able to see any difference between them.
Is that for every like value that you get, or is
You're
it
only told to do that for omega e prime, xe prime, de prime, d naught prime, and nu c prime.
okay? Thanks.
Okay. Great. So I'm going to start moving on to some of the post-lab work here. Just before I do, any last thoughts about the work so far? Great. So one of the main post-lab tasks is to fill out the table of parameters, and most of that's not too tricky because you've got given equations for k and a, and you've already calculated most of the other values. In fact, you've calculated all the other values apart from re prime. So we're going to think about re prime now. Oh, nice pink line there. So how do I want to arrange this? Just thinking in my mind. Okay, let's start with the Frank-Condon principle. Who was paying attention in Frank's video? What's the Frank-Condon principle? That's okay. So you've got a Morse potential or a potential energy surface here. They're both Morse potentials for the ground state in red and the excited state in blue. So the Frank-Condon principle says that any transitions between these will occur vertically. So the Frank-Condon principle gives rise to what's these so-called vertical transitions, like this. And the reason for this is that we say that our electronic transition happens so fast that the nuclei don't react. It's basically an extension of the Born-Oppenheimer approximation. I don't know if you remember that, if you've had any courses on valence, where you assume that the nuclei are static with respect to the electrons. Is this ringing any bells with anybody? Okay. So we can use this now, and the Frank-Condon principle now relates to the intensities of the lines that we see. So the vibrational those peaks, they get more intense and they get less intense, and the most intense one is what we're interested in. So the wave function for a anharmonic oscillator is approximately a particle in a 1D box. So if you've got distance on this one, then you've got your box. Does anyone remember what the wave function looks like for a particle in a 1D box in the ground state? So the important thing here is that it has no nodes and a single maximum in the middle. And we can transfer this onto our potential energy surface here. And we get one maximum at Re double prime. And this is where our transitions are most likely to come from. This is where our iodine molecules are most likely to be quantum mechanically, because if you square this wave function, then you get a probability distribution, and that's most intense in the middle. So this transition occurs vertically from there and hits the potential energy of the excited state at a given quantum number. And you're told that this is, I think, 545 nanometers in energy. And that allows you to basically calibrate your potential energy surface in distance. So you've already calculated the depth of it. That was dE prime. And you've already calculated how steep it is. That was related to xe prime, and you will calculate A prime when you fill out the table of parameters. But now we need to figure out where it is left to right. And that's going to be from this Frank-Condon principle, where the most intense transition comes from Re double prime and has an energy of 545 nanometers. And then there's just an equation for that. So you're given an equation in introduction where you get Re single prime is Re double prime plus 1 over A prime, and then some log of some stuff. So if I just share that part, it's 1 through 4. So there's Frank-Condon principle. There's the equation we're going to be using. Can you all see that? So all of these just need to be in wave numbers. Make sure you're using this in per angstrom, because this is going to be in angstroms. So if you've got angstroms here, you need to have angstroms per angstrom here so that you can add them together. Otherwise, it's like adding centimeters to meters. You need to convert one, or it doesn't make any sense. A meter plus a centimeter is 1.01 meters.